everybody. So today we are doing 5-4 exponential models. So we can use our algebra skills to write exponential equations when given any 2 points. We did this last week, but this time we are not doing it where x is going to be 0 for anything. Because if you look at this, you have x and y, x and y. X is 3 and x is 4, so that's not going to work for us. So let's go ahead and write out our equation. If you remember back, our equation is y equals ab to the x. So what we're going to do is we're going to plug in y, so that's 500 equals ab to the third. The other one is going to be 2500 equals ab to the fourth. Now, thinking about this, how can we put these together? Well, which one is bigger, 500 or 2500? Well, to me, I think 2500 is bigger. That's just the way it works. So we're going to take the big one and we're going to write the smaller one below it. So 500 equals ab to the third. Now, I'm going to go ahead and divide these. So divide both sides. 2500 divided by 500 is 5 equals a divided by a. Those cancel. So that's just 1. B to the fourth divided by b to the third. What was the rule for dividing exponents? You subtract them, right? So that's going to become b to the first. So 5 equals b. There you go. You got one of them. Now we're going to plug this into 1. I'm just going to do it to the 500. So 500 equals a 5 to the third. So 500 equals 5 to the third is 125a. And now I'm going to divide both sides by 125. So that tells me a equals 4. So now we're just plugging this into our equation. So y equals, we said a was 4, so 4 times b was 5 to the x. If you want to double check this, you can go ahead and plug in 4 for x. 5 to the fourth times 4 is 2500. Okay, so let's go ahead and try the next one. A surveyor determined the value of an area of land over a period of several years since 1950. The land was worth $30,000 in 1954 and $35,000 in 1995. I use the data to determine an exponential model that describes the value of the land. Okay, so let's go ahead and start off with this. So we have I here. Well, we have 2 points, right? For looking at this, it looks like the x-coordinate should be my years since 1950. The reason why I know that is because it says it right here on the x-axis. So I'm going to go ahead and write out that point, or my x-coordinate, as being 4. Because I don't want to do 1994 or 1954 because I already know it's past the 1950. So I'm just saying how much further beyond that would this be. And then my value of my land is my y-coordinate. So I'm going to put 30,000. For the next one, we're going to say this started at 5 and it went to 35,000. Okay, so now we're just doing the same exact thing that we were going to do before. So let's go ahead and write that down. We have 3,500 equals a b to the fifth power. Now I'm going to go ahead and just say I'm going to divide. So I have 30,000 equals a b to the fourth. Now we're going to divide both of these. So divide. That's going to give me 35 over 30 equals b. So we can leave it like that, or we can simplify it down and say, okay, b we also know equals 7/6. That doesn't matter, or you can get a decimal. I'm just going to leave it as a fraction for right now. Okay, so now to do the next part, we're going to figure out a. So I have 30,000 equals a 7/6 to the fourth. Okay, so that's going to give me a, a decimal. So once you go ahead and figure all that out, it's going to tell you that you're going to have 16 216.2 equals A. Okay, so what I did, I took 7/6, I took it to the 4th power, and then I divided 30,000 by that number. So my final equation is going to be y equals 16,216.2 times 7/6 to the x. Okay, now looking at the next part, part 2. That says, use your model to predict the value of the land in 2020. Okay, so very first thing that we want to do is figure out how many years past 1950 is that. So 2020 minus 1950 equals 70. So that is 70 years later. So I know I have y equals 16,216.2 times 7/6 to the 70th. Once you plug that into your calculator, you should get 787,452,500.06. You can either do this in a calculator, or I find it easiest to just pull up Desmos and just do it in Desmos, because then it's very quick to just switch out numbers really quick to see what's going on. Okay, so let's go ahead and go to the next one. So, Ohio health officials knew COVID-19 would spread exponentially throughout the population. On day number 12, March 20th of 2020, there were 169 cases. By day 13, there were 247 cases in Ohio. Write an exponential function to model the spread of the COVID-19 during March of 2020. Use your model to estimate the number of cases. Okay, so starting this off, looking at this, we have 247 cases equals a b to the 13th power, because x is my number of days, y is how many cases there were. Now the other one, I have 169 cases, a b to the 12th day. Okay, so now we're going to divide all of this. So divide both of those, divide this. 247 divided by 69. I can't really get a very easy fraction from that, so I'm just going to put 1.46 equals, the a's cancel, 13 minus 12 is 1, so equals b. So 1.46 equals b. Now we're just going to plug that in. So we have 169 equals a times 1.46 to the 12th power. Okay, so once you figure out what 1.46 times 12 is, or to the 12th power, divide 169 by that, it'll give you 2.51 equals a. So my final equation is y equals 2.51 times 1.46 to the x. For the second one, use your model to estimate the number of cases in Ohio on the 28th day. Okay, so we have y equals 2.51 times 1.46 to the 28. So plug that into Desmos or on your calculator, and it should give you y equals 100,358 cases. So I'm looking for that, and then this was my answer to the first one. Okay, cool. So let's go ahead and go to the next problem. Chase is studying exponential growth of bacteria cultures. Each is carefully controlled and to maintain a specific growth rate. So very first thing that we want to do is we want to write our function. So we're going to go ahead and write y equals 10,000, so 100,000. My growth rate here, it's a growth of 8%. So that tells me that that is 1.08 to the x power. Final number of bacteria, so it doubles after 1 day. So I have 10,000 times 1.08 to the first power. So that tells me that I have 10,800. Okay, so now we're going to write another function. We have y equals 10,000, 4%, what would that be? 0.04 to the x power. Next one, we're just going to rewrite the whole thing again. To the, how many time and days are we looking at? 2 days. So I'm going to put 2 for x. You plug that all in, you should get 10,816. Okay, so go ahead and try out the next one. We should have 10,000, 1.02 to the x. Final bacteria, 1.02 to the 4th power. So my final answer should be 10,824. And then very last time, 10,000, 1.01 to the 8th power. So 10,000, 1.01 to the 8th power. So that should give me 10,828. Okay, so we should have gotten all of those. Now, what is the relationship between the daily growth rate and the time for each culture, or the day and time? Well, it looks like as the rate cuts in half, it takes 2 times the number of days. Just to get close to that answer. Okay, so would you expect a petri dish with a growth rate of 0.5% for 16 days to have more or fewer bacteria after the initial growth? So I'm thinking about this and I'm just going to test it out. So we have 10,000 times 1.005 to the 16th day. That equals 10,830. So I imagine that it would be more, or it should be at least. Okay, so using the graph to the right, which petri dish will have the most bacteria after 10 days? So I'm just going to look at this. I'm going over to 10 days. I'm going to draw a dashed line. Which one has the highest growth rate? 8%. So 8% will have the biggest growth rate. I'm going to go ahead and end this video and we will do the last problem on the next one.